right. Hello, everybody. Can you hear me? Maybe you can raise the thumbs up.
Yes.
Thank you very much.
Hello.
Hello. So I think we just wait for 2 or 3 or 2 minutes, maybe more, because people are still joining. And then we can continue. In case you're already here, I really appreciate if I'm not only talking to empty little boxes. So in case you want and you're not shy and you want to switch on your camera, it's really helpful because then I'm not like talking to wall. Thank you. Hello, everybody. Hi. In the meantime, I can already start sharing my screen. Put this there. So I think it works, right? All right. Now we're around 35 people. Maybe 1 minute more. But then people, I think, can join. And we have enough time anyways. So it's all right. Okay, I think now we are ready to go. So first of all, welcome to everybody who is here in the tutorial at UseR Conference 2022. I'm really happy that we have the chance to give this tutorial on our package DoubleML, which implements an approach to causal machine learning called... Sorry? Okay, I think it was just nothing important. As I said, I really appreciate if you switch on the cameras because then I can see some faces, which is like much more friendly than just staring at empty boxes. And before we start, maybe a little note on our agenda for today. I hope all of you found our website where I share the materials. So in total, we have kind of 4 parts. In the first one is more like an introduction to causal machine learning based on the double machine learning approach. So this is more like a lecture from that you know from university. And in the second part, I'm going to talk more specifically on about the R package on double machine learning called DoubleML. And there I'll demonstrate our package in a notebook, which is concerned with demand elasticity estimation. And in the third part, it's your part. So you have to solve a little case study, or you can solve a little case study. We will be split up into 3 parts. That's also why it's not only my name here on the slides. So I'm Philip. Hello, nice to meet you, everybody. But also my colleagues Martin Spindler and Oliver Schacht. They will also help you during this little case study. And as a last part, we have a brief joint session again on where we summarize what we did and where we point at the next steps for you, maybe after joining this tutorial, and also for feedback. Okay. All right. Maybe one comment before we start is in case you have questions, you can type them here in the chat, and I hope that I read them in the meantime. If you realize that I'm really not seeing the chat, which can happen, please feel free to interrupt me. Also, I think my colleague Mehmet is here. And he's also having an eye on the chat. All right. And you can do as you like. You can ask your questions in the chat, and also you can put them as Q&A. Yeah, I'm happy to answer them verbally and also to type some stuff in case this is good for you. We will make some breaks in the meantime. So like after each block, we will have a brief pause. Let's see how much time we have left, but I think we have enough time today because we have 3 hours plus a little bit more. Okay. Before we start, I have a question to you. Let's try if it works. I want to make a poll, and I have 3 questions for you. The first one is whether you work in industry or academia, and if you have another field, if you work in another field, I don't know what it could be. You can also indicate other. Let's see if it works. Do you see it? I'll launch poll now. Okay. And I'm sharing the results with all of you, so you can also learn about the others in the session. Okay, let's have maybe 10 more seconds. 5. And all right, I'm closing the poll. Okay, so most of you work in academia, but it's not like only 2 people more than industry. Could also be that those people working in industry are joining later, so who knows. Okay, now I had another poll, which is on about your experience in R. Let me type it. Because I think everybody can join our tutorial, but maybe it's good to know for us for the interactive or breakout session later. So maybe you can indicate whether you're a beginner, you have intermediate experience and knowledge, or if you consider yourself as an expert. Advanced is also right. Okay, let's give you maybe 5 seconds. You have to be fast. Okay. All right, I'm going to end it. So I think most of you are intermediate and expert. So those of you who are beginners, in case you kind of have issues later when we do the case study and that stuff, especially when it goes to object orientation, don't hesitate to interrupt us and ask us. Yeah, this is why we have this breakout session system, that we can kind of account for all kind of background. So no worries. It's about like you are really able to follow my slides, I think, and join the tutorial. So nice, everybody. Now the last one, and oh, I think I can't really open it because I wanted to ask everybody. So this is not a poll, but maybe you can indicate it in our chat. I'm really curious because I like USR a lot, the conference, because it's so international. Maybe you can type in the chat where you are actually right now at the moment, because it's a virtual conference. In which country are you based? So maybe you can indicate it in the chat. I see Canada, Spain, Italy, Germany. Hello, I'm also in Germany. Hamburg, I'm right now. France, Australia, south of France. Oh, also nice, Avignon. Sri Lanka, hello. USA, it's early, I guess, for you. Brazil, nice. Thank you very much. So it's really nice to have you all here. And if there is any questions right now, you can ask me now. I have a look at the chat. Otherwise, I would start with our first part. Okay, no questions? Then we can start. So, welcome everybody to our tutorial today. We are very happy that we can give our little tutorial on causal machine learning with the double machine learning approach, which is implemented in our R package DoubleML. And DoubleML packages joint work with my colleague Martin Spindler, together with Malte Kurz and with Regression Zukov. Maybe I introduce myself first. I'm Philip. I'm currently working as a postdoctoral researcher at the University of Hamburg at the chair of statistics with applications to business administration. And we've been working on the package now for some time, and we hope that you all kind of like it, or if you don't like it, you give us some feedback. Okay, we'll start with a short motivation for causal machine learning. So I think for many people, it's not really clear what causal machine learning actually is. So here we have a little diagram to illustrate the meaning of the term causal machine learning. So you can consider causal machine learning as the intersection or like common ground for two different disciplines of research. So on the one hand side, we have the machine learning literature that has experienced a lot of innovations and advances in the last years. So you all know these new algorithms that are able to generate very, very well like well-performing predictions. Like I remember, like if you remember XGBoost, for example, for extreme gradient boosting, it has been very successful, or basically everything about neural networks. So all these algorithms and models that have been developed there, they generally follow the goal to deliver very accurate predictions. Okay, so this is one part of the literature for causal machine learning. On the other hand, we have a literature on causal inference that is concerned with modeling and investigating causal dependencies or causal relationships in data. Whereas the machine learning approaches for prediction, they are basically based on correlations, or if you maybe extend it a little bit on associations. The goal of causal inference is really to go beyond this association or correlation, and instead really shed light or insights onto the causal mechanisms in an application that you're considering. Okay, so there is a very rich and also heterogeneous literature on causal inference. There's the literature inspired and like largely influenced by Judea Pearl from computer science statistics, and also there's econometrics literature. There's work by Donald Rubin or Guido Imbens, and Guido Imbens received the Nobel Prize last year for his work on like estimation of causal effects. Okay. And in causal machine learning, we really want to combine these two literatures. Yeah, on the one hand side, we want to use or exploit this powerful performance of machine learning, which is able to consider and model very complex relationships, like they could be nonlinear, they could be, I don't know, just very complicated or high dimensional. And on the other hand, we also want to obtain results in terms of coefficient results and inference on causal quantities or causal parameters. So this is a little bit general. So I'm going to, in the next slides, I'm going to give you a more concrete idea on what causal machine learning is. Okay. To really contrast the difference between predictive and causal machine learning, I just have here a brief example from, I think, common use case for machine learning, maybe more related to, more known from practice or industry rather than academic research. So in a predictive model that we like to, where we like to employ some machine learning methods, we want to set up or build a good prediction rule, which we call fx, that uses some features or data x to get a prediction on an outcome variable y. Okay, and now consider this example, customer churn, where you really want to predict whether a customer churns or not. Okay, so the question that's underlying this approach is how can we get a good prediction rules for customers that predicts whether a customer will churn or not churn in the future. Okay, so this is really predictive. You only want to know, you have a data set or database where you have 100 customers, and you only want to know who of them is going to churn soon or not. And this is, you will set up a machine learning approach, you will choose and tune a model and really only get these predictions. Okay. And the causal machine learning approach is more concerned with the mechanisms that are involved in this kind of empirical problem. So the general question is, what is the causal effect of a treatment that we call D on an outcome variable Y? So in the customer churn example, we would like to know what are drivers for the churning decision. Okay, why do the customers churn? So this is understanding the reason for customer churn. And the second question refers to an intervention, because you don't only do it for your personal interest, but you really want to retain the customers. So you ask for intervention and you ask, how can I retain the customer? Or what can I do? What is the best thing I do to refrain people from churning? Okay, this is just a little example to contrast these two approaches. In industry and also in research, there are many cases where causality is important. So here I listed some industry cases. For example, you want to know what is the effect of a new website on your sales. If you have, for example, an online shop, will a new design of your app increase the time your visitors spend in the app, or the users spend in the app? How much additional revenue did you generate with your latest newsletter? And how would you optimally set up your marketing budget, for example? If you have different products, what is the best way to spend your money? And this is like the applied or the industry use cases, but also in academic research, there's a lot of cases where they're more like, this is the literature where these use cases are basically known better or much more common. For example, if you have, like, I have a background in economics, so there's a lot of active labor market policies, and you want to evaluate, did the active labor market policy improve labor market participation? Or in epidemiology, you might be interested to assess the effect of a treatment. So think of COVID-19 vaccination. So does the vaccine decrease mortality? By how much? So these are all the research questions. The general question in all these cases, and this is something that I will repeat in the next slides, is you are really interested in the causal effect of this treatment that we call D on an outcome that you define Y. And today we will consider two examples. And this one is the one you will be solving yourself in our breakout session later. So consider randomized experiments. So this is now in the A/B testing framework, but you can also think of this as a social experiment, or also as epidemiological, like a clinical trial. Okay, so randomized experiments are the gold standards to evaluate causal effects. Yeah, because you can, like, if you are able to randomize your treatment to individuals, then you can really compare these two subgroups, the treated and the controls. You can calculate difference in their outcomes, and then this will be some kind of valid estimate for your causal effect. Now in practice, we have some problems. So in many cases, pure A/B testings are not feasible, either for financial reasons, because, like, for example, randomizing public health insurance in the US might be very expensive, although this has been done. Or there might also be moral, like, concerns. And the other problem that might arise is that your tests or your evaluation of the experiment might suffer from low power, because even though you're randomizing your you are randomizing your treatment. This is what you can do to have a valid estimate. But maybe you only treat very small number of people, or the effect is very small, or you only have a very small trial. And you might improve your precision or your power by using some machine learning models. Okay, so in case we have problem one, we have a solution, which, like the case where we don't have the randomized trial, but we instead only have observational data. Then we might choose an identification approach. Like we set up a causal model which is based on assumptions that allows us to identify the causal effect. And this effect can be estimated using causal machine learning. Okay, so in a case where we have a selection on observables, or unconfoundedness, how it's called in the econometrics literature, we might be able to control for some unobserved, or like for some observed confounding variables that simultaneously impact our treatment variable and our dependent variable y. So this could be, for example, preferences, or individuals' risk factors or something. It can be anything. And once we are able to control for disconfounding, we might be able to identify the causal effect. There are also other approaches. Today we will only stick to this selection of observables because we only have a limited amount of time. But there's a big literature on how you can use more advanced setups there. And in the second approach, where we have an A/B test, but we suffer from low power, which means we can't reject the H null that the effect is different from 0 at the pre-specified significance level. We might improve our power by including covariates x's. Like these x's, they do not necessarily have to be related to our treatment, but instead they have to have some predictive power for our outcome variable. And if we are able to model this relationship of x and the y variable, we have a lower amount of residual variation, which means we are able to improve our precision. Okay, so this was the first example. We consider A/B testing. We have a website. We have 2 different versions, and we collect the data, we run the experiments, and afterwards we compare the 2 subgroups: those who have received a new version of a ad, for example, or website design, with those who haven't. And difference is a valid estimate, but maybe we suffer from a low bias, or we have a problem with confounding variables, which we have to account for, and then we might estimate it with double machine learning. Okay. The second example is an example on price elasticity, and this will be the example for our demonstration in the second part. So in many cases, people are concerned with estimation of price elasticity of demand, which basically tells us how the price of a product impacts the sales, or impacts the quantity that is sold. And to have interpretable parameter or quantity there, we might estimate the price elasticity theta, which corresponds to the percentage change in the quantity demanded due to the change in the price increase P. Okay, and we can set up a linear regression model in a log-log specification. So we have on the left-hand side the logarithm of the quantity, and on the right-hand side we have the logarithm of the price. And once we are able to control for some confounding variables x, the theta might be estimated consistently, which means that we are able to identify this parameter. Okay, this is an example. And here, why would we have, or why would we want to use machine learning is, for example, think of x as a high dimensional vector. So if you have a web shop and you have customers, you collect a lot of data, you know what the customers shopped before and all that stuff. So you have a lot of stuff in your data, and you might have to use some variable selection, for example, using lasso or some other approaches. That's one example. Or you could also, instead of a linear specification here, you could also plug in a more flexible specification. But I'm going back to this example later. Okay, let's sum it up. So the machine learning literature has largely focused on prediction algorithms. Okay. In many cases in industry or also in research, causal relationships are very important. And here we will know, or you will know after this tutorial, how we can assess causal relationships using machine learning methods. And we will consider two examples, the A/B test and also price elasticity of demand. And again, I repeat it again, we are concerned with the question, what is the effect of a certain variable on an outcome of interest? Okay. Is there a question so far? I don't see anything in the chat, so I think it's all right. Okay. We can reframe this causal machine learning goal in terms of two challenges. The first one is the causal challenge. So we want to estimate causal parameter. So we have to state assumptions under which we can identify this causal parameter. In the examples before, I referred to this selection on observables approach. There's also different or more advanced approaches there. So the typical problem that we have there is that in reality, we might not be able to run a controlled trial, randomized controlled trial. So we might just not be able to randomize the treatment according to to different subgroups, and then at the end just get this difference as an estimator for a causal effect. Instead, there might happen many different things or many complicated things that complicate our evaluation. Okay, so here we list some potential sources. So for example, you have that individuals, they optimize their behavior. Okay. So you self-select into the treatment that is best for you. So there's a reason why you do not choose the other treatment. Okay, so think of, for example, the COVID vaccination example. So, and remember 1 year ago when there was limited amount of vaccination available, so people really chose what was best for them. Yeah, it was just the opposite of randomization of treatment, because those who have the highest risk, they were granted the highest priority. Okay, and this is what was best for most or many people did what was most for them. So if you just think you evaluate the data as if it was a randomized control trial, you will probably suffer from a bias and make conclusions that are not really valid. So this is like one problem that in reality, especially with observational data in economics, for example, you have optimizing behavior of individuals, and you cannot really simply compare those who are observed to be treated with those who are observed not to be treated. Okay. On the other hand, there might happen many things at the same time. So you have simultaneous or you have dynamics happening at the same time. And this is a problem for price elasticity of demand, estimation for price elasticity of demand. So there are some factors that affect the supply, there are some factors that are affecting the demand for a certain product. And these things are kind of dynamic. They change and they respond to each other. So this is complicating things. There might also be heterogeneity in the population. So some people might be affected to a certain degree, and some others to much greater degree, for example. So there might be just like heterogeneity going on. We might have variables that drive decisions or the treatment assignment, as we say, and that are not observed. So this might also make things complicated. Yeah, and as I said, the problem occurs whenever we have a treatment assignment that is rather observed in the data than really generated by a randomized control trial. Okay. And as I said, I also have at the end of the slides, you can also scroll at the end, there's an example on the COVID vaccination, because I think this is an example that really makes it, or that's a common problem that all of us kind of were listening to for a long time, and that was complicated. Yeah, this was a causal analysis that was really like important for large amount of for great population. All right, so these are all the problems, but there are also solutions. So there are different approaches that allow you to identify causal effects. So for example, and this is the one we will be focusing on today, this selection on observable characteristics or controls, as we say. So once we observe all the variables that drive the assignment of the treatment and the outcome variable, once we observe all these and account for them in our model framework, we are able to identify this causal effect. Okay, so think of the A/B test. Maybe it's not. Maybe there's something driving the decision that people see the new ad or not. So maybe it's not properly randomized. Maybe people have to click through a certain path in order to arrive on this site or something. Or in the demand estimation, maybe there are some product characteristics that really play a role. And if I am able to observe them and if I'm able to really model them in my framework, I'm able to identify this causal effect. There are also other approaches. For example, there might be instrumental variables available. So the treatment itself is not randomized, but maybe the access to the treatment. Then I'm able to identify causal effect too. And there's a big literature that's expanding really, really fast. For example, you can use difference in difference estimator or synthetic control. But this is something that we will not cover here, but from like this is the point where this all kicks in, or where it becomes really handy to know these approaches. That was the first challenge. Now let's come to the second challenge, which is the big data or the estimation challenge. So in many problems, you might have a very rich data set in the meaning of having a large number of observable characteristics for an observation in the data. So the number of variables that you observe, which is commonly referred to as P, might be much larger than N. And if you use linear regression, then linear regression becomes unstable or it starts to overfit. Or the relationship of interest is just not linear, and instead you might really have to model this nonlinearity. Okay, so maybe some effects they are decreasing over time. Maybe there are some interactions effects going on from variables in the data. So this is something that is complicating the analysis from the estimation point of view. And the solution to this is the use of machine learning methods that are able to really take up these points. For example, you can use machine learning methods that perform some form of regularization, like variable selection with lasso, or shrinkage of coefficients as with ridge or something. Or you use nonlinear algorithms like gradient boosting or random forest or neural networks. So this is the second challenge, and this is the ML part. So this is the causal part, and this is the ML part. Okay, and to come back to our examples before, we use our control variables or the confounding variables axis here for two reasons. So in our data now, we have in total 3 kinds of variables. The first one is our treatment variable D, for which we want to assess the causal effect. Okay, and we have variables axis that either are confounders, which mean that they simultaneously drive the treatment assignment D and have an impact on the outcome variable Y. And we are able to estimate the causal effect of D on Y once we account for these variables X in our estimation framework. Okay, and this gives the model a quasi-experimental interpretation, which means like you can interpret D, the treatment, being assigned as good as randomly assigned conditional on the axis. Okay, or in another kind of interpretation, you can also think of this. You consider like when you estimate the causal effect of D on Y, and you don't account for X's, then it's possible that you really compare apple to oranges, because those who have been treated, they have something like risk factors or something, like they drive the decision to get health insurance. This drives the decision to get the vaccination or to enter this website with the new design. Okay, these are like driving factors for the X's and the Y at the same time. And once you control for the axis, you make them kind of comparable. Okay, so you don't compare those with the risk, with the high risk who got the vaccination, with those without risk or with the low risk who didn't get the vaccination, but instead you maybe compare those with high risk with treatment and without treatment. Okay, so this is a similar or related approach for identification. It's called matching. So basically you can match on the axis and then compare really similar cases to each other. So this is just like an outlook or maybe a help for interpretation. So because this is something I think that in practice or industry applications, many people do this causal analysis already, but maybe not with this causal framework in the back of their head, but it's just like more intuitively. And this is something where this intuition kicks in. And the second reason why this is again the case, even if we have randomized controlled trial, we can increase our efficiency by using machine learning methods, because this is why machine learning methods have been developed, because they are able to really model nonlinear or complex relationships. So in this case, we have the x variables, like now if D is entirely like unconditionally randomized, then the x's, they don't have an impact on D. So identification of the causal effect would be fine. So just comparing the subgroups of treated with not treated would deliver a result. But we can like account for variation in Y by accounting for the x's. So if we account for this relationship here from x on the y's, from the x's on the y variable, we might improve our precision. Okay, so that was causal machine learning. I hope I made it kind of explicit or clear why causal machine learning might be relevant. So causal machine learning is the field where we basically summarize all approaches that use machine learning methods in order to assess causal relationships. Okay, so there's a big literature. There are several approaches available. And with our package, we only implement one specific approach, which is a general approach, but it's only one of these approaches. And the approach is called double or debiased machine learning. So I think now maybe I do a 10-second break. If there's a question, you can also ask right now or speak up simply. All right. So what is double or debiased machine learning? Double debiased machine learning is a framework introduced in a series of studies and like summarized in a publication by Viktor Chernow-Zukov and co-authors in 2018. I have the reference also at the end of the slides. It is a general framework for estimation of causal effects, or as we say, like causal inference, that is based on machine learning. Okay, so what it will deliver, or what to expect from it, is that it will give you a coefficient estimate, for example, on price elasticity or the effect of the new ad on sales, together with confidence intervals or p-values. And in some sense, it's a combination of the strength from machine learning for the prediction and the econometrics or causal inference literature, because it's making use of the predictive performance, and at the same time it allows us to, or it makes it possible to assess causal relationships. With our package, we implemented this approach in a pretty general way, and this is why we chose to use object orientation. But this is something that I will cover in the next part. And in case you're already curious, you can go to our website where we have a lot of materials and also user guide online, as well as the reference for the R package. And there we list we document a lot. You can go through the user guide. It's like the extended version of this tutorial. Okay. Here we have a short or brief illustration on what double machine learning is. I hope you can see it, or I'll zoom in. I can't zoom in. Yeah. On the one hand side, we have the literature on machine learning where we know, yeah, oh, sorry, there's a question, yes? I think it's June?
Yeah, I just want to say that there is a question in the chat from Alexandra.
Thank you.
Yep.
Yeah, I have to. Yeah. So the question is, how do we know? So I think it relates to maybe this graph. Like here we have the confounding x that have an effect on the treatment assignment, but also on the outcome variable y. I think of this as risk factor driving the decision to get vaccination. Then also the outcome y. So in this example, or in general, how do we know whether we have managed to take all possible x's or confounders into account? Is this ever possible? So it's a good question, and I think this is a question. So once you are like the causal, like the approach to assess causal relationships is that you, and this is like something that's based on a book by Judea Pearl. In the introduction, he states this, that you set up some assumptions and you build on top of these assumptions. Yeah, once we make this assumption that we are able to control for all confounding variables, then we are able to estimate this causal effect theta. Okay. But once these kind of pillars, they break down, yeah, of course, our estimation approach will suffer from this. What you do in practice or also in research is that you play around with these assumptions. Okay, there's like an informal but also pretty formal approach now available that you vary. Yeah, you imagine like how robust is this to some maybe unobserved confounding? Like to what extent does your effect vary? If you consider these variables, by adding this or by removing this variable from the model, how does it change? Yeah, or you play around with different specifications with different models, and then you kind of know, all right, now I got everything. In many cases, you might even know how the treatment was assigned because you decide like you designed a randomized control trial yourself. Yeah, but of course, like these assumptions that are not like the crucial part, that is not a testable assumption, and this is something that gives you scope for speculation and also for criticism. I think like the important part is not to refrain from making these assumptions, but maybe to better articulate and discuss these assumptions. Okay, I hope that this is kind of making the example more clear, but we can maybe come back to this in the later or also in the break, talk about it, because I think this is like always the gate you open for the discussions. Like once you present these like causal paper on instrument variable, people will ask what happens if they do have select? What if they have access to the drug without going to this trial and all these stuff? Okay, but this is something that you never know, but you can play around with this, you can debate it, you can informally or formally assess the robustness to the assumptions that you make. Okay, now let's continue with what is the double machine learning. Do a little bit shorter. So on the one hand side, we have like the machine learning algorithms and the R packages that you know. Sorry, I think I can't. No, let me do it this way. No, sorry, it's a little bit small. On the one hand side, we have all these R packages or Python packages that give us the prediction machines like Lasso, ridge estimation, and GLMNet, regression trees and RPart, random forest by random forest or ranger package, and boosted trees like GBM, LightGBM, XGBoost. Yeah, these are all tools that are powerful for predictions. On the other hand, we have causal models that come from the literature of econometrics or epidemiology or sociology, all these different empirical disciplines that are concerned with the estimation of causal effects. This literature has developed a rich amount of or rich like shelf full of models that or approaches for estimation of causal effects, like structural equation models. There is theoretical results on identification of causal effects, like local average treatment effect if you have non-compliance to treatment assignment. There is the statistical literature that analyzes the asymptotic properties of certain estimators. And there's, of course, hypothesis tests, confidence intervals, simultaneous inference, and all that stuff. Yeah, and causal or double machine learning, in particular, kind of bridges the gap between these two literatures. So for you to give an idea on what to expect from the package is you will get, once you define your causal effect, once you state under which assumption you are able to estimate the causal effect, it would give you a coefficient estimate of this causal effect, or parameter estimate. And not only this, it will also give you some asymptotically valid confidence intervals and statistical tests for these effects. So at the end, you are able to say, under these and these conditions, I'm like the price elasticity of demand is, let's say, -1. But not only that you get this number, you also get kind of this uncertainty assessment based on confidence intervals or p-value standard errors. Okay. It is known or shown in the literature by, like in the paper by Viktor Chernozyukov, and also the follow-up studies, that the estimator satisfies some good statistical properties like root n, rate of convergence, it's asymptotically unbiased, it's also Gaussian in the limit. Yeah. And the framework can be related to the literature on causal machine learning. There's a lot of like double debiased machine learning that considered, let's say, more specific aspects of causal inference, like simultaneous estimation of multiple treatment effects. You have estimation of heterogeneous treatment effects. So there's like a big toolbox that is accessible using the double machine learning approach. So this is the goal. And now we ask ourselves, how do we get there? And what are the kind of stones that keep us from getting there easily? Okay, and I'm going to do this in a motivating example. You can think of this example as this price elasticity estimation example. Okay, consider a partial linear regression model. So this looks pretty similar to the linear regression model that we saw before. So imagine this: y is like the log quantity, d is the log price, and the axis is some confounding variable that have an effect that drive the price, but also the quantity at the same time. For example, product characteristics. Like if you have a good product, you want to pay more. If you have rubbish, you don't want to spend $1 on this. Okay. And the quantity of interest is this coefficient theta naught. Okay. And now we ask ourselves, how can we use machine learning in order to estimate this causal effect? And we might ask ourselves how machine learning enters this. And an idea would be to replace this g not from x function by some predictions based on machine learning. Yeah, because you don't know this function g, it could be nonlinear, it could be complex, there might be interactions happening and all that stuff. Yeah, so you want to use some, let's say, random forest or gradient boosting, regression trees, anything that you like, to estimate the causal effect theta. So now what's the problem? Or why do we have double debiased machine learning? Because the simple approach doesn't work. Yeah. Now, if we train a machine learning model, this estimates the relationship between y and the axis. Yeah. And we simply plug in this prediction here that we get from this, like the prediction rule from random forest. Then the problem is that the theta naught will not be estimated consistently. And why is this? The reason is that machine learning methods introduce some regularization. Yeah. As a contrast, think of the linear regression model, and we estimate simply a linear regression model here. Linear regression doesn't introduce any kind of regularization, so it's totally valid to estimate this relationship using linear regression instead of this G. But as I said, you might miss nonlinearity, you might run into high dimensional settings, you cannot really be like, there are like cases where ordinary least squares doesn't work. And instead, think of Lasso. It introduces some penalization through this L1 penalty, through this penalty term lambda. And in Lasso, it's really like tractable because Lasso really has this lambda regularization. If you increase the value for lambda, then you shrink all these coefficients to 0. Yeah. And if you use, for example, lasso to estimate this, you will at the same time shrink the coefficient associated with our treatment variable d. Okay, so this will introduce some bias. So the problem for all these simple plugin approaches is that they will suffer from regularization bias, and regularization, this will effectively distort the estimate on our target parameter theta naught. Let's maybe consider this as an example. I use a Shiny app, which you find on GitHub. It's also linked on our website, but I just demonstrated to you. Just give me a second. Because now let's see what's happening in case you use this, sorry, okay. This naive approach is loading, so now it's there. So what we see here is, I just use the tuned one. Maybe you can see it here. Now we can zoom in, yeah. What you see here is the empirical distribution of the naive estimator that I just presented, like just plug in some machine learning predictions instead of G and see what's happening. This is the empirical distribution, and what we like to have at the end is to have a standard normal distribution, which is centered around 0, because this is a centered empirical distribution, which means like if it's around 0, then we are estimating the coefficient without a bias. And here we see simulated data, like this is run on a simulation from this original paper in Chernow-Zukov, and the code is also available in the internet. On the slides you find the links. And what we see is that here we really observe this bias. Okay, here I think in this example we use a random forest estimator and just plug in these predictions for G in this partial linear regression model. And we see that we do have a shift to the left, so we don't really get it close to the true value, and also maybe a little bit skewed to the distribution. Okay, so this is something that we do not really have, because now if we look at the tails or the coverage probabilities that would result from a confidence interval that's based on such an estimator, we will make like invalid conclusion in many cases. Yeah, we might reject null hypothesis that is maybe true indeed, or the other way around. Okay. So let's continue. So this is what you see what's going on. So if we calculate the empirical coverage in this example, it will be below the nominal level. And to address this, we kind of redefined double machine learning approach in terms of 3 key ingredients. And the key ingredients, they are Neymar orthogonality, and I think this is the most complicated one. Then we have sample splitting, and we have high quality machine learning estimators. So let's start with the Neymar orthogonality. So the double machine learning approach, it's based on a moment condition. Yeah, it's a very general framework, because whenever you have a framework like a causal model that can be defined in terms of this score function psi, and the psi satisfies a certain property called orthogonality, then you are able to identify the causal effect and estimate it consistently and get the confidence intervals and all these nice things of double machine learning. Now let's consider what Neymar orthogonality is in more detail. So Neymar orthogonality refers to a property of the score function psi that is used for identification of our causal effect. So the causal effect theta naught is considered as a solution to a score function psi, or moment condition, which is here based on the expectation of a score function. We have W that denotes the data in our partial linear regression model. We have the outcome variable Y, we have the treatment variable D, and we have the confounding variable X's. The theta naught is a quantity of interest that we want to interfere, like to infer. This is the price elasticity of demand, or the effect of the new ad on sales, just to give you an example, or the effect of a vaccination. And eta naught is a so-called nuisance part, or nuisance function, or nuisance component. And you can imagine this as the part of the model that is estimated by using machine learning. Before we've seen, like, once we are able, like, we consider this case with once we are able to account for the confounding variables or to the predictors of y in the randomized experiment. Yeah, how do we account for them? And it's by setting up a prediction problem. And this prediction problem will be summarized in this eta naught. So this is the machine learning part there. Okay. Now, Neymar Orthogonality says that estimation remains valid even if we tolerate a little bit of estimation error in this nuisance component. Yeah, the true value is eta naught, and the estimate is, let's say, eta naught hat. And once we have this estimation error in this eta naught, we are still in the case, like, we still have a valid identification equation here. Okay, it's a little bit abstract, I have to say. So here's the formal description of this derivative operator. It's a Gatteo derivative operator, but let's not get too much into detail here. Let's rephrase it in a different way. Neymar orthogonality ensures that estimation of theta naught is valid even if we have this regularization bias introduced by the machine learning algorithms. We saw before that the machine learning algorithms, they introduce this regularization bias, like in Lasso, it's a very tractable case. But also the other machine learning approaches, they all introduce some regularization. And the orthogonality guarantees that the identification equation here is valid even if we have this regularization bias in our problem. Okay. So it really eliminates this regularization bias that comes from replacing the true value by the ML estimator, eta naught. It's a little bit hard to see right now, but we can go to the partial linear regression example before. I think I forgot. Oh, no, it's all right. So in the case before, we can, the partial linear regression example here, we can set up an orthogonal score there. And the score takes the form here. So on the one hand side, we have the main regression equation. This is simply rewriting this here, like the expectation of the partial linear regression equation. And we extend the estimation framework by including the first stage estimation of D on the confounding variable axis. Okay, how does it go? And this is something that we can rewrite. That's something that I'm skipping, but you can also find it online. We have it really tractable in our user guide, where I can show it to you in a second. So this is the main equation, and we account for this first stage estimation, or this auxiliary regression of the treatment on the axis. And once we do this, we have an orthogonal score. So now if you introduce some error in estimation of this or estimation of this, then you can see that the score satisfies this orthogonality property. So this is a formal requirement that is encapsulated in the identification framework. Okay, so here again, I have it in words too. So orthogonality in the PLR example can be obtained by including the first stage regression relationship. This is the regression relationship of the treatment variable D and the regressor's X. What's really handy in many cases, that the orthogonal score is linear, because this makes the computation in our package much easier. So you can rephrase the score function in terms of two components, the psi A, which is multiplied by the theta coefficient, and psi B, which is just additive. It's not working for all models, but it's working in many cases, and that's simplifying the implementation. But that's just a detail. Okay. So let's continue with this. So the first key ingredient, I think this is the most complicated one, is this orthogonality. So remember, think of this as achieving orthogonality to this machine learning bias, like this the regularization bias that's introduced in machine learning. The second ingredient that is required for valid estimation of this causal parameter is that we are using high quality machine learning estimators. So this is, from an applied perspective, it's kind of natural requirement, because you think the reason why I want to use machine learning is because it's well performing in terms of prediction. But in terms of the theoretical results, this is a requirement on the rate of convergence of the algorithm that you use. And these theoretical guarantees are obtained in many cases, or available in many cases. And it also depends on the structural assumptions that you make. For example, if you think you have a high dimensional sparse setting, you might want to use an L1 penalized learner. Or in case you have a dense setting, you might rather want to use ridge. Or in case you have nonlinearities in the nuisance part, you might want to use random forest. All these examples. I'm also, like in the app, I show you in a second, we can play around with this component and see to what extent it changes the results. The third ingredient is sample splitting. And why do we need sample splitting? And we know that from standard machine learning applications for predictions that you might run into something called overfitting, that you overlearn your data. Okay, and in more theoretical terms, it's related to complexity in the estimation, but we just refer to this to the overfitting bias. So what we would have to do is to use sample splitting in order to generate out-of-sample predictions. So the algorithm proceeds in a way that is very similar to cross-validation. So you partition the data in several sub-data sets. You fit the algorithm on the training data, and you generate prediction on the out-of-sample observations, or the test or holdout sample. And these holdout sample predictions that are plugged into the score that we saw before, and then this score is solved for this parameter theta naught. And an important or an interesting case is when you swap the roles. So you first use like let's say you do five-fold, it's called cross-fitting, five-fold cross-fitting. You use 4 partitions to, or let's say we only have 2 partitions, like you have 1 training and 1 test partition. You use the training partition, you train your ML model and generate prediction for the holdout observations. And what you can do, and this is called the cross-fitting, is that you switch the roles. So the test sample is then used as a training sample. You generate the predictions for the original training sample. And this is okay in terms of this ingredient requirement, but it helps you to use the entire data set. So you don't throw 50% of the data away. Okay. We have this cross-fitting approach illustrated in an animation. So we can watch it together. Hope you can see it. So first of all, we base estimation on this orthogonal score function. Okay. And this is required to have this valid estimation framework. And it proceeds by the cross-fitting algorithm. We first partition the data, let's say, into 4 folds. We use the first 3 as a training sample. Generate a prediction for the holdout partition. This gives the prediction for the nuisance component for this test partition here. And now we can continue this is cross-fitting, to do like to proceed fold. We can proceed foldwise. Okay, let's do this. Now we do it for fold 2 as a holdout, fold 3 as a holdout, and the others are always used as training. Now we have a holdout prediction for every data point in the data, and this is plugged in to the score function. And you see here is now 1 over n. So this is really the empirical, or the sample analog of this moment function psi. So we plug this in, and we solve for this coefficient theta naught, which is then solved here. This is a linear case, which is just a solution to this empirical score. And we can also use the quantities that come from this estimation approach to calculate a standard error and confidence intervals and p-values and all that stuff. And as a theoretical results, these are stated in this study by Chernow-Zukov and co-authors, that under certain conditions, the double machine learning estimator, theta not tilde, is asymptotically normally distributed. Okay. So here we have the references. And you can, it's on the slides, you can watch it yourself and step by step go. Now let's look at our simulated example. Where is it? There you go. So we can now step by step add it's like a recipe. We can add the ingredients. So first of all, let's look how this estimation, like the empirical distribution, changes if we use an orthogonal score here. So before we used like the non-orthogonal, like just the plug-in approach corresponds to non-orthogonal approach. So now we use an orthogonal score and we see, all right, not that much change. So it's still not looking really like the Gaussian distribution, standard normal. So we can also introduce some sample splitting. Wait, I have to choose this. Some sample splitting. So we see that we still don't get it because the last ingredient is missing, the high quality machine learning. Here I implemented, like, this is the results for 3 different specifications of machine learning method. For example, the tuned one is a tuned random forest. And for this one, which looks good, so it's well approximating the underlying relationships, we see that the empirical distribution is now very close to the nominal, like the theoretical one. But if we use instead a regression stump, which heavily underfits the data, we see that even with orthogonal score and even with sample splitting, we have a bias and a non-centered distribution here, and or asymmetric distribution maybe. And also if we have overfitting, we don't get it too. So we need all 3 of them. We need the orthogonal score, sample splitting, and a well-performing machine learning algorithm. And now you can also, we have, like, we're in 2 minutes, we are having a break. You can also play around with it. You can download the app, and I can paste the comments to run it on your machine in the chat. You can also look what happens if I remove the sample splitting, what if I have sample splitting, what if I drop the orthogonal score, and all that stuff. Okay. Okay, so that's it for now. I would say we take a break of maybe 10 minutes, 5 to 10 minutes, and you can play around with the app. I have the link to the repository here. And you can copy the commands here to the chat, and then you can run it on your computer immediately. You just have to install Shiny before, and the remaining packages, they are installed on the way. Okay, once you have questions, you can type them now in the chat, because now we are done with the very first part of the tutorial, which is the introduction to double machine learning. In the next step, we talk about the double package 4. Okay, thank you very much.
I've got a question.
Yes.
So you mentioned in the beginning that double machine learning is like one method of estimating the treatment effect, but there are others. Can you, so does that imply, I mean, is the implication that it would be better to use double machine learning in some contexts than others?
It's a difficult question, but a good one.
I'm just, I apologize if it's
so there are very
reflection.
different approaches. So there are some that are more related, and some others that are like more like different. For example, the literature at the beginning of, like, when people asked or like studied how to use machine learning in order to estimate causal effects, a lot of them focused on lasso. Yeah, and there are many approaches that are based for lasso. For example, there's something called also the biased lasso, which is very similar to the double machine learning approach, because what double machine learning really does, it gets rid of this bias. So it implements the debias step. So this is similar. So if you go for one or the other, it's maybe the difference is not that huge. But the double machine learning approach has an example, like it makes it possible to use also learners that are different from LASSO or from L1 penalized or L2 penalized estimators because of the sample splitting aspect and because of this analysis. Okay, so this might be an advantage or generalization there. But there are also very different approaches. I think there's one that's called, oh, now I hope I'm not mistaken, like selective inference is something developed by Tipirani and co-authors, and they consider a very different setting. It's a different meaning of the results that you get. So the interpretation of the p-value is different there because you condition something on the selection set that you have that's produced by LASSO, and you try out different model specifications, selection results, and that's something from interpretation perspective. It's different. Yes. So there are different approaches available. It's really hard to say one is better than the other. It's rather maybe asking for what do you want, like what is the reason why you want to use it, and what is the interpretation you want to give to it, and is there something, yeah. So double machine learning can, of course, do a lot. Like it's a general framework in case you are able to phrase your estimation problem in terms of the orthogonal score. You're able to make use of the results. But in other cases, you just are happy with the different kind of result. You don't need p-values, but you just want to. So, for example, there are these meta learners that are available from Künzel and co-authors. I think they're available. They give you insights on heterogeneity of facts, but they have a different interpretation in terms of the results that come. So if you have a different perspective, you want to use another approach instead. So it's really hard to say. I'm not blaming any approach. I mean, like, yeah.
No, thank you.
Thank you for the question. Yeah.
Sure.
Okay, I think there were 2 questions in chat. I'm going to answer them right before we start again. So let's meet here again in 3 minutes. All right, so I hope everyone is coming back again from the break, because I think there are still 3 questions that that I haven't answered. Is this right? Oh no, this one. Here there was one question on the variable z or z here in the Neymar Orthogonality or in the theoretical framework. And the data W, as I said in our example, we only have the outcome, the treatment variable, and the x variables, which are like the confounders or control variables. And in some models, you can also have an instrument. And this instrument is called Z here. You can also, like, it's not a definite notation here, but in general, you can also, if you are familiar with instrumental variable estimation or estimation of local average treatment effects, there you have instrumental variables, and they are helpful to identify causal effect, which has then a slightly different interpretation maybe, but that's something that's totally that's feasible, that you define the score function in an instrumental variable model too. Okay, then someone asked, what is the overfitting in the app? So let's go again to the case where we have combined all key ingredients. So the requirement on the high quality machine learning estimator is that that the estimation error in the nuisance component is small. Small means like in the limit, it's kind of you can bound the variation on true value. That's the theoretical explanation. In practical terms, here in the app, I wanted to illustrate that you cannot simply plug in basically all kind of machine learning method. Like you can that the machine learning part has to comply to certain quality standards. You know, like that you have that the machine learning method does not overfit or underfit data, because I mean because the performance of this machine learning part, it will the predictive accuracy of this machine learning part, and that's something that we can play around in the interactive session later. You can just plug in a regression stump, and regression stump is very likely to underfit the data. Okay, so if in case you only plug in a regression stump and you want to approximate a complicated regression relationship, which is underlying here, then you even have the first, like the orthogonal score ingredient, the sample split ingredient, but the machine learning part is missing because regression stump is not good enough in order to approximate these nuisance functions. Okay, now let's go to the other case. So it's not only that you have an algorithm that is too simple, but also that you overlearn or that you overfit your data. Okay, and here the overfitting part, I ran a gradient boosting, and I used a very a large number of iterations. So you know that if you run gradient boosting, you update it again, then you run to overfitting, and this is illustrated here. So this is the learner that we use, and I think it becomes maybe clearer when we go through the example notebook in a second. Okay, now there's another question. Are causal models basically regression models with constraints on the conditional expectation? If not, what are the differences? I'm not 100% sure if I can answer this like right away. But I see where it goes. You want to kind of have an idea on the causal model. So the causal model is something that is specified based on your qualified judgment as a researcher in a certain area. Okay, so you think, all right, I know that here I have a clinical study and I have a new treatment or new drug that people want to have, but I cannot maybe force people to participate in the study, but I can randomize the access to this drug, to this new drug. Okay, and this is something that has to be taken into account by your causal model, and it's not really like a refinement on the expectation of your on this regression function that you incorporate, but instead it's rather like which regression equations you want to or you have to estimate in order to come up with this final model, like in order to get this causal parameter. And then in this case, the partial linear regression score or model might not be enough, but instead you might have to introduce an instrumental variable approach, which corresponds to a different score function. Okay, so you do not really say that your conditional expectation here is something like you do not make functional form restriction or something or constraints, but instead you have to kind of add the model ingredients to each other, like the equations, the moment equation that you need for identification of the causal effect. Yeah, but maybe we can come back to this also later. I hope that I kind of could at least say what what it's not. Okay, good. Are there any further questions? Okay, if not, then we can go to our notebook, to our next part. There you go. So now we talked about the causal, the general approach of double machine learning. It was like a theoretical introduction, more or less. Now let's talk about the implementation. So how can you really do it in practice based on our package 4R? Okay, so let's start with our building principles. Now, our building principles, these building principles, they kind of match the key ingredients, because the first ingredient we remember is the orthogonal score. And the orthogonal score is something, as I said, in many cases it's linear. So it's something the double machine learning approach is very general. So we can implement this approach in a general way if we make use of an object-oriented implementation. Yeah, and this is why we chose R6, because then we can set up a class structure that I'm going to explain in more detail in a second, that runs these steps of the cross-fitting algorithm that I showed you before. There was no, we didn't mention in this video on YouTube which model we used, because this approach is general. It doesn't matter which causal model you use, if it's instrumental variable, if it's regression, linear regression, partial linear regression, if you have non-parametric estimation of treatment effect or something. So this is something pretty general, and this generality is something that we can use or implement in an object-oriented way. Second ingredient was a high-quality machine learning methods, and there we have an interface to the MLR3 universe or ecosystem, because there they have a unified interface to the most important machine learning libraries in R, and they also have a lot of different tuning methods available. And the MLR3 ecosystem is growing really fast. So they added, in the last years, they added more and more packages and more things that are helpful. And to use sample splitting, we use also built-in functionalities of this MLR3 package. So this is making it possible to access or to use a great range of different specifications with one double machine learning implementation. There was a question, what's the difference between sample splitting and cross-fitting? Yes, so the sample splitting itself is something that the sample splitting is the procedure that we make a difference between the training sample and the holdout sample. So we fit on the training sample and we generate predictions on the holdout sample. So this is basically sample splitting as you know it from a holdout approach. What is cross-fitting? By cross-fitting, it just means that we swap the roles afterwards. Okay, so this is the extension of the sample splitting. So you can run all these. So you can also in the interactive part Janeth, you can ask your instructor how to do the case without cross-fitting, because also you can estimate all models without performing cross-fitting. Maybe because it takes too long, maybe, I don't know, you don't want it, you just want to have a separate thing, a separate sample partition and that stuff. So it's also possible to do it in the package. But as I said, the cross-fitting, and I have it here in the as a second illustration of our app. So this is the now uncentered distribution of the double machine learning estimator. And this is without cross-fitting. We see that there's a certain variation in our estimator. But if we use cross-fitting, it's getting like this, the degree to what, like it's way more centered or more concentrated around the true value if we use cross-fitting by swapping these samples. So this is like the empirical advantage from using cross-fitting over sample splitting. Question? Yes, and cross-fitting corresponds to k-fold cross-validation. That's how you can think of this. So it's basically doing k-fold cross-validation. The extension is that we are not only interested in these predictions, but we have these predictions and then we plug them into the score. So this is like the cross-fitting, maybe. I think there's no formal definition of the cross-fitting. It's just like how it's called in the original paper, so we call it cross-fitting. You can also think of this as cross-validation, I think. I hope I don't offend anyone with this statement. Okay, so let's talk about dependencies. We have the key dependencies are the MLR3 dependencies to MLR3. And in MLR3, we have the sample splitting implemented and a bunch of functionalities, but in MLR3, there are only very limited amount of learners available. And you can access these learners by the additional packages like MLR3 learners and MLR3 extra learners. But this is not a dependency of our package, but you can use virtually any kind of learner that is provided by these packages because they pass the requirements made by the MLR3 ecosystem. For tuning, we have the MLR3 tuning dependencies, and R6 we use for object orientation, and data table is used as for data handling. But this is also in line with the MLR3 package universe because they also rely on data table, and R6 too. Why did we choose an object orientation or object-oriented implementation? As I said, in many cases, the score is linear, which means that theta is corresponding to something like a expression that is based on psi A and psi B, or psi in total, overall. And this is independent of the model class that we consider. It doesn't matter if we use partial linear regression model or if we use the instrumental variable model. And also it's possible this is something that we are currently working on, a difference in differences, for example, it's also something that can be represented in terms of this linear score. Then we can implement all the procedures for inference based on this abstract or general score psi. Okay, so basically you can extend the package in any way by any kind of model that has such a score representation with the orthogonal score. So this is really handy for the implementation because we only have to implement the functions used for inference once, and all package model, all model classes can use it. And this opens gives us the opportunity to also base estimation of standard errors, computation of confidence intervals, also a bootstrap procedure, multiply bootstrap procedure that is used for simultaneous inference in general. The sample splitting can also be done in a very general way, and all that stuff is implemented in abstract base class DoubleML. So this is the stuff that we can implement in this abstract base class. So this is the general part, but there's also model-specific aspects, and these the parts of the models that are model-specific are the nuisance components. Yeah, so the partial linear regression model has a different score function and different nuisance components in this than an IV model, for example. Yeah, so this is all implemented in model-specific classes that are that inherit from this base class. So here's a illustration of this class structure, and currently we are supporting 4 different models, but we are currently working on extensions. So we have this like estimation of effect is implemented in the abstract base class in a fit method. We also have this bootstrap for as p-values or stuff for multiple testing. And also we have confidence intervals. All that is implemented in this abstract base class. And then we have different subclasses like model-specific classes. For example, are we considering partial linear model? And then you can go through all these cases. Like, do we have an instrument to variable or not? If you don't have it, then we end up in the partial linear regression model. And this is associated with a particular score function. So the score function is here. There are different scores available also for partial linear models. So consider this one here. And this is also a difference, maybe, June. This is also answering your question. So if you have a linear, if you have an IV model, then the score function looks different. So this is a difference in the causal models. So here we have the nuisance part, for example, predicting the treatment variable D based on covariance X. So this is nuisance part M. And you have the main regression of Y on G. This is the nuisance part G. And these nuisance estimation parts and also tuning for these components, this is done and implemented in the subclasses. So we have the partial linear regression model. We have the partial linear regression model with instrumental variable. We have so-called interactive regression model that that features heterogeneous treatment effects. So they might differ for different individuals. And you see here the score looks different. This is a doubly robust score. And you can extend this to IV score to estimate local average treatment effects too. And all these models, they differ in terms of the nuisance estimation. Okay. So the advantages, I think I already said this before. It makes it very flexible. So in case you want to have cross-fitting or not, you can just use the option and like adjust the estimation framework to your problem. There are different algorithms available. You can also vary or provide customized resampling schemes, which might be interesting in some cases. And it's easy to extend because you can, like, if you add a new model class, then like maybe a variant of partial linear instrumental variable model or something, then the only thing you have to do is, except for taking care of all these technical things like exception handling and stuff, you have to customize the nuisance components part. Okay, and once you're done with this, you can make use of all the features provided by our package. Okay, now let's get started with our DoubleML package. I hope you read the installation guidelines in the Getting Started guide, so you have installed the package. Otherwise, you can do it right now. I think I added the link just on top of this chat, but I can also insert it again. If anyone raises their hand, I can do it. You can, like, there's no difference in these two versions right now because we released last week on Cran. And we will consider an example of demand estimation. So let's consider this causal problem that we want to estimate by how much the quantity of a particular product changes, or a bunch of product changes, in case the price changes. And we use a data example that is a real data set from an online retailer that was hosted on Kaggle. And we kind of reframe a blog post, which is online here. The link is like, you can click on this, jump on the blog post. We just redo his analysis or part of his analysis based on our package. Like the causal part, this is something that we provide you already, also in the interactive part that's starting soon. So here we take an observational, an identification approach that is again based on this observation condition control. No. conditional on observational characteristic approach, so selection on observables. That was the word that I was missing. So we want to account for some confounding variable x's, and they comprise the product characteristics, for example. So we generate some features that are able to model similarities between variables, between products. And once we are able to control for these variables, then we are able to identify the causal effect of this variation in price on the variation in quantity. So this is the causal quantity that we want to infer. So now let's jump to the notebook. And I have the notebook here as a HTML file available, so you can run it in your console. In case you replicate the analysis, don't get afraid if it takes some time, because the problem is pretty high dimensional. I mentioned it in a second. So it takes some time. Maybe you can adjust the set of variables, and then it's easier, it's faster. And you also have it as a Markdown script, so you can run it immediately in your RStudio session, and also as Jupyter Notebook if you like to work with this. Okay, so let's get started with this notebook. Okay, there was one question, but I think I'm going to answer them after the sessions. Okay. So let's start with our example on estimation of price elasticities with our package DoubleML. So as I said, what we want to learn in our example is the price elasticity of demand. This corresponds to the coefficient theta naught. And this indicates the change in the quantity of a product due to the change in the price of this product. Okay, and these changes, they're not absolute changes, but relative changes. So this is how you do it, how you state elasticity in your introduction to economics classes in your studies. Yeah, so this is like the theoretical quantity that we want to infer. And in order to estimate it, we pre-process the data. So you in Notebook you can inspect it again after the workshop too, because the notebooks, they are available and online. We come up, so we rephrase this regression problem in terms of a partial linear regression model, where on the dependent variable is the log change in the quantity. On the other hand, we have the explanatory variable, which is the log change in price. The log quantity is the dependent variable, the log price is the treatment variable of interest. And here we use machine learning in order to flexibly account for this confounding x. And yeah, this theta naught is again the parameter of interest that we want to estimate. Okay. Now, in this setup, this notebook is now organized according to a so-called, like we called it a workflow for DoubleML, because it really gives a, we hope that it gives a tractable structure on how to perform an analysis with our package. Because first we start with the backend, then we initiate the learner, then we pass this learner to a model object, we initiate a new model class, and we run the analysis, we make conclusion and all that stuff. Okay. And I hope this is like, in case you have prior experience with object orientation, maybe it's all right, but in case this is the first time that you get in contact with object orientation in R, I'm going to shed light on this in a second. So how do we proceed? In the very first step of our workflow is to really formulate the causal problem. So that goes to the question that came up before, what is a causal model? So the causal model is really the set of assumptions that we make in order to identify our causal effect. And here we took this approach that we, like this selection observables approach. So for now, let's assume we are able to account for all variables that simultaneously affect the price and the quantity. Okay. Now, the question that came up before, what happens if we don't? Okay, we can play around with this. For now, we live with this and say, all right, this is valid. We trust in the author of the notebook before, and I think, okay, once we are able to account for product-specific effects, like or seasonality. Yeah, could be that on Christmas people start to buy Christmas presents. Then it's different for some people. Okay, so first, once we are happy with our problem formulation and we said, okay, let's trust this partial linear regression model, it will identify our causal effect. Then let's continue with our analysis, or we started by initializing a data backend. So what does it mean? First of all, we load the data. And here we have an example of the raw data set. It's just a short example. It's not a full data set, just to save some capacities. You can just copy paste this code in your R session and you will have the same output. This is data that we use, and we see that it's data from 2010 to 2011. It's collected until the end of 2011, I think. It's data on sales across various countries. So here we have France, United Kingdom. There's also Australia in it and stuff. And we have product descriptions. So you can copy paste these product description and find out that these are, I don't know, funny products. Now this is like the online retailer, and it's like fancy pens and funky design tapes and that stuff. So it's really interesting, and it's real data set. So you find that this is actually not a made up data example, but it's real data set. And we also observe how at a certain date, how many units have been sold, and how much revenue has been made with it, and how much was the price at this date. So we have variation in prices as well. We have quantities observed, that stuff, and we use this data in order to estimate price elasticity. We did some data pre-processing out of this outside this notebook, so you can read it up again, and in case you have questions on this, you can also contact me afterwards. And here I listed the data that we have in our pre-processed data set. So we have something like quantity, revenue, unit price, month of the sale, day of the month, day of the week, how many days the product has been sold in the online shop, what's the average price of the product. We have dummies for the date. We have country dummies. We have also, and this is maybe interesting, it's a n-gram constructed to account for product description and similarity in this product description. So here you see this feature description. So it's basically text, and you can process it in a way that kind of pens are maybe closer or more similar to other pens than to hats or something. And the result of this is a matrix. I don't remember the dimension of this matrix, but it's kind of big matrix. Okay, and we have changes in prices and changes in quantity. You can download the data set from this URL and look at the data. Now it's pre-processed. The names are not super nice. We just transformed them in a way that they work with R. Yeah, and as you say, it's only a subsample of the original data. We only picked 10,000 observations. And oh, the notebook, where can you find it? Good question. Here I have it. Thank you for this question. Sorry for being late. Ah, yeah, someone already inserted. So it's online, this notebook, yeah? You can click here on this website and find all the materials. This green markup is indicating that there's a link below. So we have 10,000 observations and 900 variables in the data. Okay, so we have this high dimensional, or like, it's not like 10 variables, but already many. Okay, here we look at the columns again and the data. This is everything that we now start to work with. The DoubleML package, the object orientation, it is based on several steps. So first of all, you initialize a new data backend. Okay, and this data backend corresponds or is implemented as an object class called DoubleML data. In this data backend, we specify the data that we want to use. So here before, we loaded the data And the data set itself, it's called demand data. Okay, it's a data table object, and we can pass it to our data backend initialization stage. Okay, so now this object class knows what data to work with. Moreover, we indicate the role of the variables. Like, what is our dependent variable? It's the change in prices. What is the treatment variable that we're interested in? It's the change in the log price. Did I say? So dependent variable is the change in the log quantity, and the treatment variable, or the variable for which we want to infer the coefficient, it's the change in the log price. And we base our estimation on our selection observable approach. So we feed in all the variables. Here I collected all the names. Here I collected all the names of the data sets that do not correspond to the dependent or the treatment variable in this feature names character. And I just pass it to our backend. Can increase the font again. Now what will be, so we initialize it by calling the new method for this class. And at the end, as a result, we will get an object called data DML. And we can print it and look at the summary. So it says, all right, you have now a data backend. Here it's data DoubleML object. And we have a short summary for this method, for this object. Treatment variable as we indicated. And here you can see the list of all variables. It's many variables. They are not nicely named. So I hope this is all right for you. So you can hear really all variables in there. So here's 551. This is the dimension of this Graham matrix. Okay. And you can also read off which countries are here. But this is like, it's a little bit messy output because we have so many variables. And we generate in an automated way. Okay, so now we have the data backend. In the next step, let's the causal model. We already said before, we have the problem formulation, and it will give us the idea of a model class in DoubleML. So this is really now which model to choose, and we choose the partial linear regression model with a log-log specification. This is something that we write out here. This now really reflects the partial linear regression model that we've seen in the introductory part before. Okay, so this is the main equation where we would like to infer the causal effect of the log price change on the log quantity, provided we control flexibly for characteristics x. And the auxiliary regression, or this first step regression, is stated here because this is what we need to get our orthogonality. This is just like the same, just reflects what we've seen on the slide before. This also tells us something about the nuisance parts that we have to estimate. Okay, so we see that here there's this function g or g naught, and here we have this function m naught. And together we can combine them, or we can collect them in this nuisance part eta. I don't have it on this notebook here, but this is something that you can now keep in mind. Eta corresponds to g and m. So these are both parts, or these are the regression relationships that we have to estimate it, or that we want to estimate with machine learning methods. Now the next question is, what do we use as machine learning methods? And here in this example, we have 3 different specifications. And you can experiment it in the breakout session in a second. You can use learners that you like. Yeah, you can stay with default parameters, or you can also play around with, I don't know, number of iterations of gradient boosting. And in this example, we'll consider 3 different methods or learners, and they are now taken from MLR3. And this is how you can nicely initialize a learner from MLR3. You call this function LRN. It's an abbreviation or acronym for learner. You specify what kind of learner it has. Here it's either reg for regression, so it's a continuous outcome variable, so regression problem, or you can also use classification in case you have a binary variable. So then you have classif here. But that's something that's you can read online. And the second part tells you what kind of estimator you use. And LM is the standard LM package or call that you know from the basic, the stats package from R. It's a linear regression. So this is maybe a benchmark that we want to use. You can also use cross-validated lasso with a certain specification of the penalty based on a GLMNet package. And we can also use random forest here in some specification. I think we took it from the original notebook using Ranger package. So I hope that you kind of see the major idea on how to set up learners using MLR3. But I also have more information on this on the slides in case you're interested. Now we have a data backend and we have the learners. Now we have to feed these two objects into our DoubleML framework. And this works through the model class. So here, DoubleML PLR is the model class that implements the partial linear regression model. So what we've written in terms of the equations, regression equations above, this is also like mirrored by this object class in R. And you can choose some options when doing this. So you can, for example, choose the algorithm on how to calculate the coefficient estimate. You can choose a score. You can even provide a self-specified score. You can choose the number of folds and even number of repetitions on how many times you want to repeat a cross-fitting. But we stick with the default options here. So we can initialize now a model class, like an object of a model class partial linear regression model, by passing through the data backend and the learners. And then we are done. Okay, so here we have for all three learners, we specify a different object. So here, the partial linear regression model based on the linear regression learner. We have the model that corresponds to the lasso learner, and we have the model that corresponds to the random forest model. Okay. And now the rest, or the remaining part that we have to do is just to call the methods for this class DoubleML PLR. And this is the part that's inherited from the abstract base class that I've shown you on the class structure visualization. Okay. So you can estimate or perform the estimation of your coefficient using the fit methods. We use here this option to store the predictions because then we can evaluate the accuracy in the nuisance predictions. Okay, and we can use now we fit or we estimate the three different specifications that we've defined here. And the first one we do is the linear regression model, and we already get a warning because I think it depends on it's due to the dimensions of the data that this already said. Oh, it's in German. Sorry. You have to be careful because the matrix doesn't have full rank. So this is something that I'm not sure if you have seen this before, but this happens in case you have a high dimensional problem with linear regression. So we can run the fit command and then summarize our estimation with the summary call. And we get an estimate for our causal effect. So estimate for our causal parameter, the elasticity, based on the linear regression estimation, it's minus 1.84. We can now compare this to the results from lasso and random forest, and we see that the estimates, they are kind of close. Okay, so here we have minus 1.81 or 82, and here we have minus 1.81. So they are all in a similar range. Okay. And now we can basically start with the conclusions. But what makes sense sometimes, or I think in many times, in order to see what's going on in your model, especially in the hands-on example that you'll see in a second, is to find out what's going on in nuisance part. And here we calculate the predictive performance for the two nuisance parts, so for this main regression and for this auxiliary regression, or the first stage regression. And this is a helper function that calculates the RMSE for both of these regression problems, we apply the estimation to all the model to all models and the components. So we have MLL, this refers to the main regression, and MLM, this remains to the first stage estimation. And we estimate them, and we can summarize them and plot them. Okay, and what we see is here the linear regression model, it has a way bigger RMSE than the lasso and the random forest for the main regression. And now I can decrease the font again. And for the first stage regression, we see that lasso is maybe performing a little bit better. So this just to give you an idea on how does machine learning add to estimation of treatment effects here, because we see here that based on this data that we use here, random forest and lasso kind of make sense in that they are able to better predict the nuisance components involved, like the main regression here and the first stage or propensity score regression here. You can also do more diagnostics, but like this is just to illustrate you how to proceed. Okay, and the next step 7, is inference. So let's now summarize the results that we have. We have different model specifications and we summarize them in some way. So here we plot the estimates that we have and we make our final conclusions. So this is also the part which is basically done outside our package. So this is done by human like you. So in all 3 model specifications, we've seen that that the estimated coefficient was close to minus 1.8. And we can also plot the confidence intervals. And we see that they are pretty tight, so they do not cover the 0. So we can say that our coefficient is significantly different from 0. So price elasticity of demand here amounts to, or the estimate on this price elasticity of demand is around minus 1.8. And yeah, it's significantly different for 0. You can expect more. You can now consider, like you can continue your analysis, look for heterogeneities, model specific, I don't know, for any kind of thing, but this is just like an exemplary illustration on how to use the package. Okay. And I would recommend you to open this notebook because it will help you during your session. Okay, so let's continue. Because now we continue with the interactive part. So you will be now assigned to breakout session. Like after we make a little break, I'll assign you to breakout session to my colleagues who are already in the call. So Martin is there, Oliver is there, and Mehmet is also there. Hello. And you have the opportunity.
Hello.
You have the chance to practice your DoubleML skills there. And as I already mentioned this case study before, so we will look at the evaluation of A/B testing, where we have to take confounding variables into account. So we have their confounding variables, which are called V, and they drive the assignment to this new ad design that's going to be evaluated. And the dependent variable is sales in hundreds of dollars, doesn't matter. So our causal approach is again accounting for confounding variables V. The data that we use is not really like from an A/B test, but we rephrase it as an A/B test because I think in many cases this is kind of a practical or tractable example, and it's taken from the 2019 Atlantic Causal Inference Data Challenge. So it's a data set that's randomly chosen. So we did not select the one which is particularly nice. Okay, and one difference, like the notebook is set up in a pretty similar way to the demand estimation notebook that I just presented. There's one difference because we have now a treatment variable that is binary, and we will make use of a different model class. We will not use the partial linear regression model. This would be possible too, but just to give you a little bit of an extension is we will use a so-called interactive regression model, but it's documented in, like I mentioned it in the notebook. You will see it and you can read up the online documentation and run estimation there. Okay. Before you start, after the break, I give you the links to some resources. So there is the link to DoubleML workflow, which is also listed on our website. I'm going to paste all these links here in the chat. There's also a user guide that explicitly or that explains the model class and also how to initialize the data learner in the data backend again in more detail. You can also use the demand estimation notebook, as I said, as a reference. We have the documentation of the R package online via this link here. And we also have a paper, but I think the paper is maybe too long for the amount of time that we have. You can open the slides again and find a very brief quick start to R6 in case it's the first time for you to work with R6 classes, because here I explain how you can initialize it and what's the idea behind it, just very briefly, and how to call methods and access fields. And also how to debug in case this is interesting. Also how to create learners in LR3. I have a brief note here, and also a link to the reference, I guess. Or I can send it to you in case you're interested. Okay. So now I would say we take a break. I shared a link with you, and I set up the breakout session, and you will I'll assign the breakout sessions after the break, because I forgot the questions. I'm going to answer the questions before we start with our breakout sessions. So let's meet here again at 1:15, so in 10 minutes. We'll briefly discuss the questions and then start with our tutorial, okay? And in case you have questions, you can add them in the chat. Thank you. So now, before we start, we have a bunch of questions left. I go back to the question, I don't know, maybe you'll just wait for a second longer. As before, I mentioned that in many cases you have a linear representation of the score, and there was a question in which cases the linear score does not apply. So in which cases we do not have linear score. And in a development version, we, I think, even support nonlinear scores. So there are some cases where you do not, where the where the linear score does not really hold. I remember that if you consider copular models, I think you end up with nonlinear score. And Martin, you can help me. Was it nonlinear? No, it's linear.
But copulars, I think it's a good example, and more complex models, it gets in nonlinear scores, but this is in development. So many important models, IV, all have this linear representations are now in the package, but the next step is to extend for nonlinear scores.
Yes. Then the question was, to what extent does DoubleML identify, solve, mitigate the issue of bidirectional causal effects? And that's something that's not done inside the DoubleML approach. So you can set up a causal model where you indeed have bidirectional causal effects. So A affects, or D affects Y and Y affects D. But you have to come up with a framework that you can identify the causal effect in some way.
But this is maybe only to add, this is how tricky, because, for example, in all the stack literature, by definition, it's not allowed. So you have to define a causal effect in one direction. If you have reverse causality in two directions, it really gets tricky. I think for DAGs, there are now recent research papers, but it was considered as almost impossible what to do. So having this is really quite challenging how to model this. But not only for DoubleML, but as I said, for DAG, by definition, the DAG it's excluded.
Yep. Then there was a question, what is the partial part of partial linear model? So where do I have the partial linear model? Here, the partial linear model is defined as a model that is partial linear and partial nonlinear. Not really helpful, this explanation. Now,
we do not see your screen yet.
Oh, sorry. Oh, thank you for this. There you go. I hope now you can see it. Yeah, now you can see it. Thank you. This partial linear model is, and this is maybe not the best example. I go back to this. So this partial linear model is linear in the treatment variable D, but nonlinear in the axis. So this is why it's partially linear. Partially linear means linear in the treatment and nonlinear in the axis. There was one question.
Maybe here.
Yeah.
Not sure, Philip, if you already addressed this, but here we consider always D as one treatment variable, but of course you can have many treatment variables, and this is also covered in the package. So you might have not only one price elasticity, but you might have several cross-price elasticities, so that you have not only one treatment variable, so that you have many treatment variables. This is no problem at all. The only thing here applies is you might run into multiple testing issues, because if you have, let's say, 100 price elasticity at the same time, want to do inference, then you need to do corrections for multiple testing.
Yeah, and that also already answers the other question with multiple decoys. Yes, that's possible. In the partial linear regression model, we support this. Yes. There's a difference between between the different nuisance parts. I think just to recap this here. So we specified two learners here. One for the nuisance part MLL, which is this main regression in the partial linear regression model. So consider this equation here. This is subsumed in this nuisance part MLL. And the other nuisance part LMM really refers to this equation here, to the one that we have to include in order to get orthogonality. So each model classes is defined in terms of its nuisance component, and this is something that you find in the online documentation of our package. So you can go here, open the reference for each model class, and here we go to the partial linear regression model, and you find here the explanation on the nuisance components in the documentation. Okay, so you can read it up here, and then in the notebook that you're solving now, you use another model class, and it's also defined in terms of some nuisance components you can find there. The variance, that's another question. Is it derived from the score? Yes, there's a formula that's based basically on the score. I think I leave this for now. Yes. And in case you have more questions, you can ask them, of course, in the tutorial, or we will recap them afterwards. Okay, in case you are not happy with my explanation now. Now I'm going to assign you to, before we go to the breakout rooms, let me maybe briefly introduce my colleagues that are going to take care of you. So one breakout session will be moderated by Martin. He's professor of statistics at the University of Hamburg with applications in business administration. He's also a developer of our package. And then you also have Oliver Schacht as an instructor. He's a PhD student for statistics, and he's working in causal machine learning and causal reinforcement learning. And he also works a lot with our package, so he's going to be a good instructor for you. I would like to say that we will meet here again after the breakout sessions, because we will have final sessions where we will give you kind of the information on the next steps, and where we can where you can get a hexagon sticker. I'll tell you more about this in a second. So now enjoy your breakout sessions, and yes, see you here later. Okay, and there you go. I think you have to click on join here on the right hand side. Then welcome back. I have to share my screen again. Yeah, it works. I think some people are still missing. All right. I think we can continue. So I hope you kind of made your steps. with our package, because now we have like 30 minutes to go, and I hope you all kind of made some progress in the notebook and helped you to kind of get a better impression on what the package actually does, how to use it. I don't know if it was said in all tutorials, we share the solution, and I think also in the chat it's already there pasted. I'm going to share it there again. I think it's already here. So you can read up again and find out how it compares to your solution, because there's not one solution, but like everyone has its own solution, and yeah, there are many approaches that you can take, like specifying some options of your model and that stuff. Okay, so let's briefly recap and finish our tutorial for today. First of all, congratulations, you just made your first steps in causal machine learning with double machine learning. So I think, I hope with this tutorial, we gave you a better impression on what causal machine learning can do for you, or what it actually does. And in case, and we can briefly summarize what we did today, we introduced the basics and the challenges of causal machine learning. We provided an introduction to the implementation with our package DoubleML, and you solved a hands-on example. Like there were 2 examples, the price elasticity example and also the A/B testing notebook. So what's next? The outlook. So you can continue to learn about our package by visiting the user guide. This is a link. You can click on the link, or I shared it also in the chat. And of course, you find it here on our website too. I don't know, I think I closed it. And you can continue finding out more about the details, or like about like the next steps really. For example, you can find out how to adjust sample splitting, how to tune your algorithm. You remember from the Shiny app that I showed you for the basics of double machine learning, there had the 3 cases where with a nicely fitted regression tree or random forest, with the underfitting algorithm based on a regression tree or regression stump, and an overfitting learner based on gradient boosting. So in case you want to learn more about tuning the parameters, there's also a section in our user guide. There was a question on how to do inference on multiple treatment variables. So there's also a chapter on simultaneous inference. In practice, clustering standard errors is really important. So you might have, this might be helpful for you. And of course, there are also other model classes. We didn't talk about instrumented variable models here in detail. So that's something that you can find out more. Also, we have a paper on the R package, which might also be helpful for you. I have it as a reference at the end. In case you further work with our package, we are really happy to hear about bugs. And in case you have questions, it's really like, we opened up space for discussions on GitHub. So we frequently look at it, and we are happy. And also there's a tiny but growing community discussing solutions there. So maybe to give you an idea on our next steps, or you can also be part of our next steps, because we are really welcoming extensions and contributions to our package. We are currently working on a bunch of extensions. So some of them are more related to the causal part or the double machine learning part, like extending the estimation, like the estimation framework to heterogeneous treatment effects, like conditional average treatment effects or group average treatment effects. There were also questions on this today. Extensions to the built-in resampling schemes, because there have been some papers on how to refine the resampling. We also are working on extensions of model classes, for example, difference in differences, categorical treatment, partial linear IV models, and also AutoDML, which is automatically debiased machine learning step. And we are adding continuously examples to the gallery. So the examples is like the demand estimation or A/B testing notebook. Moreover, we are opening the interface to MLR3. So there has been done a lot on more advanced tuning schedules, and also there's something called autotuner, which we want to support in our package. As I said, we're really happy if you contribute to the package too. Like even reporting bugs, opening issues, and discussions, that's already helping us because we have better impression on what we can do. And also in case you like to, or you work on adding model classes, in case you adjust some parts of the model, add a parameter or something. In case you want to add a replicable data example too, we are happy to add it to our gallery. And yes, we have contributing guidelines online. I insert the link here. These slides are available, as I said, so we are happy to hear from you if you want to contribute a little bit. Now I tell you how to get this hexagon sticker. So we have these nice hexagon stickers, and we thought that it might be a nice little incentive for you to give us to share your feedback with us. So please, you can open this link. I share it in the chat too. You can click on it and provide your feedback. And at the end, as a thank you, you will see a link where you can insert your address, and we will send a sticker to you by mail. And in case you don't want to give your feedback, you can also reach out to us, and we will send you the hexagon sticker because these are really nice, and we still have a bunch of them. Okay. In case you have comments or questions, or you want to contact us because you have some extensions in mind, we are really happy to hear from you. So send an email to either Martin, Oliver, or me, or to my colleague Malte, who is also who is also a developer of the package. So I would like to thank you for your patience, for your active participation, for your solutions to the notebooks, and for all the questions. Here we would like to thank some people who helped us preparing this course. So Malte and Victor, also Mehmet, Anthony, Gangli, Joshua, and Georg, and also the contributors of the data challenge at the ACIC conference because they allowed us to use the data. And at the end, I added references. And yeah, with this, I would like to conclude. And in case there are questions, we are really happy to answer them. Is there any question? I have a look at the invalid dynamic link. Yes, I inserted the link again. So there were some questions. Yes, of course, the slides and the materials, they will be available online. Also, the GitHub repository, in case the data, the website will be down, it will be provided in the repository for the materials. So no worries on this. Let me have a look at the questions. So there's a question to contributing to the DoubleML package if we have some references. Yes, you can click on the contributing guidelines, and there we listed references too. So we include references to the R package, or advanced R books by Hadley Wickham. I think there's also a new edition coming out. Also, we link to MLR3. to the references and the book and online resources there, because they're really extensive and helpful too. Also
Maybe
up and that stuff. Yes.
maybe to add, if someone really has more time or finds this interesting and wants really support us with programming some parts, we are happy. So reach out to us, and then we can define some submodule which you can contribute. So if someone is eager on object-oriented programming and is interested in the stuff, so feel free to reach out to us, and then we can maybe define some well-defined sub-project.
Yeah. And even if you don't have that much experience in object orientation and just start with functional implementation, that's already a good start, because based on this, we can also work out together a solution on OOP or the like inclusion in our package. So the recording, there's also another question. I think we agreed to publishing it on YouTube. I'm not sure about the last part about the interactive breakout room, if this is feasible, but we'll talk to the organizers and yes, share the video afterwards. And in case you have Twitter, I recommend you to follow the Twitter account of USR Conference, because there they always announce news. So in case they publish the videos on YouTube, I think it takes some weeks. Until they publish all the talks and all the tutorials, they will let you know about it and you'll hear about it. And then you can come back to the tutorial and go through it step by step. Okay. Any other questions?